Welcome, everyone, to an introduction to deep learning with TensorFlow. We'll wait a minute or two before a couple more people to come in. So let's start at 6:35. In the meantime, you can enjoy the meme. We'll be starting in just a minute. Just out of curiosity, have any of you taken the machine learning course yet or the computer vision? No. Some beginners. That's great. It's mostly for beginners. The less you know, the better. All right, well, let's just get started now. I don't think anyone else is coming. So, this is an introduction to deep learning with TensorFlow. So, AI is powering more and more technology, and at the forefront of AI is deep learning, with TensorFlow being the library of choice for those who. So, for those who are looking to see if AI is something they may want to do, or if you already want to get into it, then this workshop can be a great introduction. So, what will you learn in the next hour or so? We'll start it off with some history on how deep learning came to be, why it's even needed in the first place, what a neural network is, what a convolutional neural network is, then the more practical portion on using TensorFlow to create an image classification AI. Then we'll end it off with some next steps for those wanting to learn more, and then some questions. So if you have any questions along the course of this workshop, try to save them, as it probably will be answered later on in the lecture. So who we are. Wayne?
Hi, everyone. Wayne. So, along with Ritesh, we'll be co-hosting this TensorFlow workshop today. I am a fourth-year student here at Ryerson in the co-op computer science program. And my experience with machine learning started very recently, actually. So last semester, I took creating a web app. And while the web app is pretty simple, the heavy lifting was kind of done behind the scenes.
Wayne,
What we
you cut
did
out a
was
bit.
we
Could
created
you
an app.
repeat it from the start?
Oh, yeah, sure. I was saying that, yeah, I'm a fourth-year CS co-op student at Ryerson, and my experience with machine learning started recently. And it started when I took the ML course last semester. And what my group and I did was we built a web app, and most of the heavy lifting was done behind the scenes with our machine learning model. And what it did was it took in over 400,000 listings for used cars, and it would predict the price of a used car given its features. So the app, as you can see there, you can put in the make, the model, manufacturer, the mileage, what year the model is, the transmission, the color, things like that. And given these features, it would predict the price of the car. And we got it down to an accuracy of roughly like plus or minus like 3 or 5% of the actual price of the car. And we thought that this was a really good use case because generally when you're buying a used car, it's very easy to accidentally like pay too much or pay too little. You don't really know if you're paying the right amount, right? So that was our driving force behind pursuing this specific project.
And I'm Ritesh. I'm a third year in CS. I'm currently on co-op, my third term, working at Blue Cat as a software engineer intern. I haven't actually taken the machine learning course or computer vision. So unlike Wayne, my experience with deep learning has been self-learning for about the last year or so. And especially at my last co-op term, I was actually working on a project by myself where, because I worked at the Ministry of Transportation, and so we had access to all the cameras throughout Ontario. And so I found out that we previously tried, because how it is right now in the summer, there's a certain 2 week span where there's actually people sitting down watching recordings and using a clicker to click how many cars and trucks pass in the highways for data collection purposes. So I thought we could automate that. And so I used TensorFlow and PyTorch to build a vehicle detection and tracking system with automatic lane detection. So I got it to a point where there's actually a team working on it now after I left. So that's pretty cool. Now, with everything new you learn, you have to learn some history behind it. So weirdly enough, deep learning dates all the way back to the 1940s, when Walter Pitts and Warren McCulloch created a computer model based on neurons and the networks in the brain. The whole idea was that we perceive the outside world through simple neurons and their connections. Therefore, with enough logical networks of knots, ands, and OR gates, one can represent every conceivable finite function. It only now appears to be called deep learning because it's gone through so many different names and so many different viewpoints. So a complete history is beyond the scope of this workshop, but some basic context is useful for understanding deep learning. In short, there's been 3 waves of deep learning that deep learning has gone through. The first is cybernetics in the 1940s to 60s, and next is connectionism in the 1980s to 90s. And then the last is the current resurgence under the official name of deep learning beginning around 2006. Some of the earliest learning algorithms we recognize today were intended actually to be computational models of biological learning, where neuroscientists, they wanted to figure out how does our brain learn what we learn. And so because of this, the name artificial neural networks was first created. So cybernetics is based on two core ideas. First is that the brain provides a proof by example that intelligent behavior is possible. And second, which is most important, is that because intelligent behavior is possible, the straightforward path to building intelligence is to then reverse engineer the principle behind the brain and why the brain works and duplicate its functionality. So the story of the first perceptron happened in 1958 in the US Office of Naval Research. So the US Office of Naval Research unveiled an IBM 704, like one of those computers back in the day that filled like an entire room. And so they fed it a series of punch cards. After 50 trials, the computer taught itself to distinguish cards that had markings on the left from cards that had markings on the right. This was a first demonstration of a perceptron. Now you'll look at what perceptrons are later. So the creator Rosenblatt stated, this is a first machine which is capable of having an original idea. This is the first machine that learned by doing. Despite being very promising, it was quickly proved that perceptrons could not be trained to recognize many classes of patterns. So that caused the field of neural network research to really stagnate many years before connectionism came into existence. So connectionism proposed a feed-forward neural network, you'll see what that is later, or a multi-layer perceptron, which consisted of two or more layers. The addition of more than one layer provided great processing power than just a single layer. And the second reason, which is probably one of the biggest, is that why deep learning saw a resurgence was because the replacement of linear activation functions with nonlinear ones. We'll get into what an activation function is later on also. During this time, neuroscience's role in deep learning was diminishing. The main reason for this is because we simply don't have enough information about the brain to use it as the guide. To obtain a deep understanding of the actual algorithm that our brain uses, we would need to be able to monitor the activity of at least thousands, if not tens of thousands, of neurons simultaneously. And we're just not there yet. But that doesn't mean neuroscience hasn't helped the field. In fact, there's a study done back in 2000 where it found out that ferrets can learn to see with their hearing region of the brain if their brains were rewired to send visual signals to that area. Now, this suggests that our mammalian brain might be using a single algorithm to solve most of the different tasks we see it solve daily. So neuroscience has given us a reason to hope that deep learning algorithms can solve many tasks at once. So what exactly is a neural network? Where does that leave us today? Before this hypothesis of a single algorithm, machine learning research was very divided. It had different communities of research studying natural language processing like Google Translate, for example, computer vision, like image classification and object detection, like your Tesla car does if you have a Tesla car, speech recognition, and then generative AI. Today, these are still separate, but it's very common for deep learning researchers to study many or even all these areas simultaneously. So why use deep learning? Why not just use machine learning? With deep learning, your actual output of your model isn't limited to a certain form factor. Your model can output stuff like text, sound, images, and numbers as well, whereas machine learning models are limited to only numerical form. Deep learning also generalizes better with less data given and can learn the underlying patterns in the data better. On top of data, unlike machine learning methods, deep learning continues to grow with more data you provided. As Andrew Ng said, and for those of you who don't know who Andrew Ng is, he co-founded Coursera. Coursera is a website which gives a lot of courses for free, and he teaches deep learning to like thousands of people. And I would say it's one of the best deep learning courses that's free, alongside Stanford's free course on machine learning. So he said that the analogy to deep learning is that the rocket engine is the deep learning models, and the fuel is the amount of data we can feed to these algorithms. Another major reason for choosing deep learning is because of the so-called curse of dimensionality. So dimensions, which you will most commonly hear in the field as features, are basically the number of inputs you pass into your model. So for example, if you have an AI that classifies which dog breed you're most compatible with, and that AI has 3 dimensions, those 3 dimensions could be like your gender, your age, and your height. Or for example, if you have an AI that classifies images, as you will in this when using TensorFlow, into different categories, you're passing in images, and suppose you're passing in images of 100 by 100 in size. That's a total of 10,000 dimensions, as each pixel value would be its own dimension, its own feature. So you can clearly see how the number of dimensions can scale up with problem complexity. On top of this, more dimensions means more possible configurations that are possible. If you look at the image at the bottom, for example, it shows how a single dimension classification tasks, you only have to worry about one input value. So let's say that input value can take on 10 different possible values. An example of this would be like a number line from 1 to 10. When you add another dimension, you exponentially increase the number of configurations possible. There's 10 possible input values left to right for the first dimension, and 10 possible values up and down for the second dimension. Giving 100 different combinations that are possible. With 3 dimensions, it's 1,000. So you can see how it increases exponentially. And this is a challenge because it becomes noticeable with machine learning when the possible configurations is much larger than the number of training examples that you provided to train on. Now, some machine learning models attempt to address this by assuming the output of some new training data that it hasn't seen before will be near the nearest training point. Now, deep learning is impervious to this curse. The reasons why are too in-depth for the context of the workshop, but if you'd like to know more, then feel free to Google about what the manifold hypothesis is. Now, finally, let's get into what a neural network is. In the most basic form, it's functions stacked onto one another. Like in grade 11 and grade 12, you learn about composite functions, where the output of one function gets passed in to the input of another. So in this example, we know what X is, right? That's the input you pass in, like a previous example of a model that took in 100 by 100 images, then the input X would be 10,000 units of measurement or features, which contains a pixel data. Then what exactly are the functions and how do they modify our input? A function is a layer of nodes. And so neural networks are composed of these layers stacked on one another. Now, you remember how I said multi-layer perceptrons? Initially, the first perceptron created had only one layer. Then when MLPs came in, they had multiple layers, as the image you see here. So the first layer is called the input layer, where the neurons in the input layer contain the values of the features. For example, if you represented an image in black and white only, right, and we're passing it into our model, right, the first input, right, could be like 80 and 10 and so forth, where 80 represents how dark that pixel is, 80%, 10%. And then after this follows the hidden layers or actual functions where we manipulate each input in some way. Then after the hidden layers, it connects to the output layer, which contains the actual output of what we want, whether that be a singular neuron containing a binary classification like, is this a dog? Is this not a dog? 0 or 1, right? Or a bunch of neurons containing like the bounding boxes for object detection. Now you can see a common theme here that there's a lot of connections going on, a lot of lines between the neurons, between the nodes. In fact, all the neurons each neuron is connected to each and every single neuron in the next node. So the actual flow of input X starts with the input layer being filled with each feature from X. Then at each layer up to the output layer, each node will perform some sort of calculation, and you'll find out what that calculation is on its value, and then pass it to each neuron in the next layer. And by the end of it, at the output layer, it should contain the answer we want. So I'll quickly touch briefly on some of the calculations that our network will perform. So there's two sections of calculations that happen. For those that happen on each forward pass, and then those that happen only when you're training. I'll go more in depth on the first section since it's more important. So if you have a look at the diagram on the right, the green circle represents a neuron in a network, and the blue circles represent neurons that are connected to this neuron from the previous layer. So how exactly do we get the value that the green neuron will pass to the next layer? We take the neuron values connecting to the current neuron, multiply each of them with the respective weights, and then add them together. Now, if you look here, if those who took linear algebra, this is similar. This is exactly the same as the dot product. So for example, in this case, it'll be x1 times weight 1 plus x2 times weight 2 plus x3 times weight 3, so on and so forth. After doing this summation, we will then offset it with a bias. Each neuron has a bias. The bias is a constant factor. It's a constant, and it acts as an additional source of having an impact on the value. So all we do during the training process is we're going to be altering the weights and the biases so that by the end, at the output layer, we have the value that we want. Now, after adding the bias, we put them through an activation function. The activation function gives our network the ability to learn some nonlinearity. Without a nonlinear activation function, you'll just be multiplying x, the input right here, with the weights plus the bias, right? This is the exact same equation from the slope of a line, y equals mx plus b, where m is the weights. And no matter how you add the lines on top of one another, the end result will still be another line. For example, let's say you're adding 1x plus 1 with 2x. The result will be 3x plus 1, and that's still another line. So no matter how many lines you add, the end result will still be linear. Now that's a problem. Suppose that's a problem that I'll actually show in the next slide. So having a nonlinear activation function afterwards gives the network the ability to learn nonlinear problems. And as for which activation function, there's quite literally dozens to choose from. However, the gold standard right now is ReLU, or a modified version of ReLU. It's very simple. It's just the maximum between 0 and the value you're passing into the activation function. So all the way to negative infinity, it's just sitting on the horizontal axis, and once it hits the origin, or 0, 0, it just becomes a straight line, y equals x. It's very simple, and because of the simplicity, it makes it easier to train, and it uses less calculation required, which makes it faster. So now let's also touch on some calculations that happen during the training process. So initially, when we train a neural network, we initialize its weights and biases with random numbers. So obviously, if you pass in or inputs, it would perform pretty bad because it's basically noise. But how do we quantify how bad? This comes from our loss function. Our loss function tells us how bad our model performed. So we would want to minimize the loss function, minimize the loss. There's lots of loss functions, and there's each to be used in certain scenarios, with new ones popping in from research fairly often. And so the loss we get from a loss function, again, is to what we want to minimize. To minimize it, we would need to change our network's weights and biases in a way that would minimize it, obviously. And this happens when we use an optimization algorithm. The most common one is called stochastic gradient descent. SGD is an improvement on gradient descent, which happened in the early 2000s, but gradient descent itself was first theorized all the way back in 1847. For those of you who have experience in machine learning, you use gradient descent already for linear and logistic regression. And so the optimization algorithm points to a certain direction where we need to go. But we still need to update all the network's weights and biases to go in that direction. And to do this, we use something called backpropagation. So after a forward pass, you get the loss, you pass that into the optimization algorithm. The optimization algorithm tells you which direction to go. And to actually update the weights and biases that would make it go in that direction, backprop goes backwards through the network from the output layer to find the changes needed on a per neuron basis on its weights and biases, and then make that change. Now, this is an iterative process. Gradient descent won't give you the exact weights and biases required to find the absolute minimum loss. Instead, it points slightly towards the right direction, or what it thinks is the right direction, or else it would overshoot if you try to make it go too far. So as a recap, during training, we initialize the network's weights and biases with random numbers. We do a forward pass through the network. We get the loss by passing in the output to our loss function. We calculate the direction we want to change our weights and biases with our optimization algorithm. Then we actually go backwards through the network to change them. So this forward and backward passing, this happens thousands, if not hundreds of thousands of times, depending on how big the problem is, the size of the model, the size of the data. And we do this until we think it's a good point to stop the training. Training itself may take minutes, hours, weeks, depending on all the factors I mentioned, and depending on whether you're using a CPU or whether you're using a GPU. Because GPUs, they're really good with simple matrix multiplication. And as I said before, the dot product is a matrix multiplication. Now let's look at this video, which shows actually how nonlinear activation functions actually allow you to learn complex problems. So I'll actually change the speed to 2 because pretty slow. I'll skip through it a bit. So let it just pause. Okay. So this number you see here, that's just the weight, and this is the bias. And it goes through the neuron, and then it gets activated with the ReLU activation function. Now you see when the weight is 1, it inputs 1, the bias is 0, it looks exactly like the ReLU function. Now, as you see, if you change the bias, it gets shifted a little bit. You change the weight, tilts the other direction, right? Now, if you combine it with another one, you can start to see how different shapes can be formed. So now let's pause, start from here. And so here's a fully connected neural network. For the sake of simplicity, let's not worry about all those random connections. They have an effect, but for the sake of simplicity, let's worry only about a select few of them. And you will see how slowly, by modifying the weights and the biases of each of these neurons, can we actually make it learn the sign function. So I'll skip through it a little bit. You can see it learns the top part, and then it learns to go down, and then it'll learn again to go back up, and then until finally it'll change the bias a little bit to shift it up and down, so it's exactly like a sine function. And as you can see, as the input, this is the x, this is only a one-dimensional input, goes increases and decreases, you can see how some neurons are activating more than others. And at the end, it gives the y value, which is the output we want. And so you can actually see this in action. Now Wayne will take over from here for convolutional neural nets.
Hey everyone. Okay, so I will be covering convolutional neural networks and TensorFlow and the second half of this workshop. So a convolutional neural network, or CNN, no, not the news network, but a neural network. It is a deep learning algorithm that's most commonly applied to analyzing visual images. So this will be our focus for today, and that's what we'll be building soon when we use TensorFlow. So generally, neural networks use matrix multiplication, and CNNs, they use convolution, which is a mathematical procedure in at least one of their layers. And I'll go over what layers are in just a bit. So these special neural networks, CNNs, they were inspired by the connectivity in our popular applications
Wayne, could you go
include
back
image and
like
video
30
recognition,
seconds? You cut
things.
out.
Oh, sure, yeah. I was saying generally neural networks use matrix multiplication, whereas CNNs use convolution, mathematical procedure, in one of their layers of the network. And I'll go over what layers are in just a bit. So these special neural network CNNs, they were actually inspired by the connectivity of neurons in the visual cortex of animals. So popular applications include image and video recognition. So things like Face ID, image classification, even medical image analysis. So generally doctors would try to study dozens of x-rays and try to see, oh, does this patient have an abnormal growth in their lungs or anything like that? And recently, CNNs have been used to create applications as an assistive tool when diagnosing. So you will feed the CNN tons of images, tons of x-rays, and you'll label them with the presence or absence of a tumor. You'll say, hey, this is an image, this is someone's x-ray of their lungs, this one has a tumor, this one does not, this one does, this one does not. And eventually it is able to detect tumors when presented with new images. That's the key term. You have a set of images that you learn from, and then a new set that you test on. And at its simplest, a CNN will take in an input image, right? So check out the boat in the bottom left. It'll take in an input image, which is simply an array of pixels, and it will feature map this image into individual layers. So at the first part, it'll split it into red, blue, and green. So if you could go to the next slide, actually, so I can show them the animation. Yeah, so it will split the data and assign importance through learnable weights and biases. Ritesh was talking about learning these weights and biases to assign them to each neuron. And eventually you'll be able to differentiate, the CNN learns how to differentiate one image from another. And CNN learns small features at first. So it might detect, in terms of like facial detection, it might detect small features like lines of a nose bridge, lines of a cheek, things like that. And then it'll learn more and more complicated features like the shape of your jaw. And then finally, through a series of convolutions and pooling and connected layers, you'll get a resulting output. So in this GIF that's playing on screen now, you can see that the original image, however large it is, has been split into 3 channels. There's a channel for red, green, and blue. And there is something called a kernel or a filter. And this filter is, as you can see, it's a 3x3. So this 3x3 little filter will move step by step, as you can see. It goes from left to right and then down a layer and then left to right again. It'll move left to right and it will perform matrix multiplication with the values in the image. And then you'll get values, it'll generate values in the output. Okay, so that's just something that happens behind the scenes while it's learning from the image. And if you go on to the next slide. Okay, so now we're going to talk about TensorFlow. So TensorFlow is an open source AI library that was developed by Google for internal use to accelerate machine learning and deep neural network research. So it did start off internally, but it was released in 2015 so that it was available to the public. And it is mainly used for classification, identifying images, perception, understanding. It's used in things like self-driving cars, that kind of thing. And it's really easy to use because it has a ton of pre-built functions and advanced operations. And that's what makes it easy to build different types of neural network models. So we're going to be using TensorFlow because it's more suited for practical applications. You might ask, hey, I've heard of this thing called really generally more suited
Wayne, you
for
cut out
practical
again. Could you go
applications.
back 30 seconds?
Oh, yeah, sure. Sorry if I've been cutting out. My internet's been acting up a bit. TensorFlow is mainly used for classification, identifying images, perception, and understanding. And it has applications in self-driving vehicles, things like that. And it has a ton of pre-built functions and advanced operations, which make it really easy to build different neural network models. And we'll be using TensorFlow. And you might be asking, hey, I've heard of this thing called PyTorch. Why don't we use that instead? And PyTorch, while it is a great library, it's really popular, it's more oriented towards research, whereas TensorFlow is more suited for practical applications. Okay, so I'm going to share my screen and let me know if you guys, give me a sec. Okay, do you guys see my screen? Okay, cool. So yeah, we will be using a tool called Google Colab or Colaboratory. So Google Colab is a powerful tool that you can use to build neural networks. And you can interleave these types of markdown. So where you have text like this, and you can interleave them with code blocks. And that makes it really easy to document and build models. So for today's workshop, we'll be using something called, we'll be using the CIFAR 10 dataset, which is a huge data set of images that are typically used for these CNN models to classify images. Okay, and we'll also be using the Keras sequential API to create and train our model. So I will be sharing this link with everyone after the workshop so that you can run through this yourself and train the model. So to begin, what we do is we import this library, right? We're using Python, so we have this import statements here. So we'll be importing all our dependencies that we need. Okay. And next, what we will be doing, so in order to import it, we have these code blocks, right? All you have to do is click on this play button here. Okay, so we've imported TensorFlow. Next, we need to download this data set of all these images, okay? And what we're gonna do is we're going to split our data set. Remember how I said we have to first train our data set and then we test it? So in order to do that, we can't train and test using the same set of images. We need to split them up into a training set and a test set. Okay, and this is important because if you have these two mutually exclusive sets, this is what allows us to train and evaluate our model, our algorithm. Okay, and that's how we can observe how accurate it is. If we, oh, notice we have a typo here. If we just used one set, then our model would simply be memorizing. It wouldn't be learning from from the images, right? It's just memorizing what they are. So if I click play here, this is what will download the CIFAR dataset. Okay, and I think I've already done it, so it should be okay. And something else we do is we normalize the pixels in the images. Okay, so we normalize them to be between 0 and 1. And this just ensures that among all the images that we have, some might be big, some might be small. This ensures that they're all appropriately fitted. They're all scaled well. Okay.
And just to
We do
butt
that.
in,
Yeah, go ahead.
the reason why it's 255 is because pixel values range from 0 to 255. So when you divide it by 255, it'll be from 0 to 1.
Yeah, thanks. Okay, so next what we're going to try to do is verify the data set. Just as a class.
No, way, cut out
class.
again.
We said we're going to. Sorry. I said next we're going to try to verify the data set. And to verify that it looks correct, we initialize this array of classes. Remember how we said we're going to classify images? We're going to put them into 10 different groups. So these are the 10 types of images we're going to see: an airplane, an automobile, a bird, a cat, etc. Okay. So when I hit play, it's just going to print out the first 25 images in a grid. See if I can zoom out a bit. Yeah, the first 25 images, and it's just going to label them according to its labels. Okay, so you can see while they may look blurry, they are appropriately labeled. You have a bird, a horse, a ship. Okay, so now let's get right into it. Next, what we're going to do is create a convolutional base. Okay, so this base is basically what our model is going to be. So we create this base. Remember how I talked about layers? So the CNN has multiple layers, and in this model, we're going to use a conv2D and max pooling layer. So the conv2D layer creates your kernel or filter. Remember that 3x3 grid that was moving side by side in the GIF I showed earlier? The conv2D layer is what creates that. And the pooling layer allows us to reduce the dimensions of the image by taking the max or the average of a few samples as we move across. Okay. And in this case, we're going to be using max pooling. Okay. So as an input, the CNN will take in tensors of shape, and we ignore the batch size. And the color channel
Just to butt in
refers
again, a
yeah.
tensor is just an array. It's a fancy word for saying array.
Yeah, thanks. So in this example, we'll configure our CNN to process inputs or images of the shape 32, 32, and 3. And I believe the 3 refers to the RGB, if I'm not mistaken. Okay, so here just in the code, you'll see we're having 32 filters, okay? And the shape is 3x3, just like we saw in the GIF. The activation will be ReLU, just like Ritesh mentioned. And the input shape is the images, right? So 32 pixels by 32 pixels. Okay, and then this is how we're doing the pooling. So we just click play, and I think I already ran this in the past, so it should run. And next we just display a summary of our model so far. Okay, so here we can see that we have our conv2D layers and our pooling layers. And as you can tell, the output of each conv2D and max pooling layer is a 3D tensor. It's a 3D array of shape, height, width, and channels, right? And the width and height, as you can tell, it's 30, 30, 32, then 15, 15, 32, then 13, then 6. They get smaller as you go deeper into the network. And the number of output channels is controlled by this first argument right here. See, 32, 64, and 64. Typically, as the width and height shrink, you can computationally afford to add more output channels in each. And as you can see here, we have 56,320 trainable parameters. So think of 56K different dials and knobs and switches that we're trying to adjust in order to make our model learn from these images. Okay. Next, we add something called dense layers. Okay, so dense layers just mean that each of the neurons in the previous layer is fully connected to the next one. Okay. And this is what we do to perform this classification. So dense layers will take in a input, which is one-dimensional. But remember we said that the output of the previous layers are all 3D. So we need to flatten it. We need to, whoops, sorry about that. We need to flatten it and make it into a one-dimensional array. So that's why we do layers.flatten. And then we have these two dense layers here. So the first activation is ReLU and the second one is softmax. And over here, we set it to 10. I'm gonna look at the chat real quick, or maybe Ritesh, you can look. Can anyone tell me why we have 10 output classes? Oh, my bad, I literally highlighted the answer. So Cypher has 10 output classes, right?
You cut out again.
This array. No, why is my internet bad? I was saying that in this final layer, we have 10 outputs, and this is because we are classifying 10 classes, right? Airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. That's why we have 10 output classes in our dense layer, okay? And again, we print out an architecture of our model, right? And we can see that our 4x4
You didn't
64
run
outputs were
the previous
flattened in.
cell.
Oh, did I not? Oh. There you go. Okay. Oh, there we go. Yeah. So our
You ran it twice. No.
Is that bad?
Yeah, you ran it twice. You added the flattened dense again. Just run it quickly. Run from top to bottom.
Run from the top. Okay. Sorry. Just give me a sec. 1, 2, 3. Okay, there we go. Sorry, I think I double clicked last time. But yeah, so our outputs are now flattened into the shape of 1024 before going through 2 dense layers. And now what we do is we finally compile and we train our algorithm, okay? So we run our machine learning model over 10 epochs. You can see here at the bottom, you see epoch 1 out of 10, epoch 2 out of 10. These are just, you can think of them as rounds of training. And after each round, we will get a loss, we will get an accuracy, and the weights and biases that we had before get back propagated and readjusted, okay? So the more rounds we run, generally we expect our model to do a little bit better, right? So you can see the loss seems to be getting smaller. The accuracy was 0.33 and it's jumped up to 0.71 now. And we'll just wait for this
In the meantime, you can see
to finish.
In the meantime, you can see the optimizer that's used is called Atom. That's a slight different variant than SGD. And the loss is called sparse categorical cross entropy. And then all the metrics we're using is just accuracy.
Mm-hmm. Okay, so we've trained our model, and now let's go ahead and evaluate it. So here in this code block, we're just plotting the accuracy of the model based on the training set and the test set. Okay, so here you can see, obviously on the training set, the training accuracy happens to be a little bit better than the test accuracy. And if we, there you go. If we print the test accuracy, we can see that it's roughly 70%. And that's pretty decent for just a few lines of code. And just to begin, this is not bad. Yeah. And once I share the link, you can check out all these hyperlinks through here to learn more about the sequential API, how exactly the conv2D or max pooling layers work. And yeah, that's...
If you scroll to the bottom, the graph there for those wondering why we split the training and testing data, we split it with a certain percentage. Usually it's around 80% of our data we use for training and 20% we use for testing. And so when we train, our model never sees the testing data. We only use the testing data to see the real world performance. So if you look here, initially the training and testing, they both improve together. But later on, the testing stagnates, but the training will continue to improve. And that's because the model basically memorizes the training data. So when you just memorize stuff, you won't actually be able to apply it to a real world scenario. And so this is why you have to, when you make deep learning models, you have to configure it in certain ways that are more standardized, and you may even configure it in ways that you want, so that the testing accuracy, the point that the training and testing accuracy diverge, is very high, which yields a better model. You can stop sharing your screen. I'll share mine.
Okay. Yeah, I'll pass it back to.
Okay. All right. So next steps and resources. So there's a couple resources that you can use. There's a deep learning book by Ian Goodfellow. For those of you who don't know who Ian Goodfellow is, if you know those face swap apps, you know, like where there's like you swap Elon Musk's face with Tony Stark, right? Or like what Snapchat uses, all those things, the backbone of it is called generative neural networks, right? They're called GANs. And so he was the creator of GAN. He created GANs back in when he's doing his master's, and he's actually director of machine learning at in Apple. So he has a very popular book called Deep Learning, and it's basically all theory. There's almost no practical things in terms of like actually coding and using actual frameworks and whatever. There's none of that. It's all theory. It's very long. It's around 700 pages. And I'm also reading, which I suggest, is neural networks from scratch in Python. Now, this is more practical. This is also very long. In this book, you basically create your own deep learning framework. Now, you're never really going to use this framework. You're going to use TensorFlow or PyTorch, right? But when you go through this book, you find out the inner workings of deep learning frameworks and the actual how each little thing is done. Then there's also courses you can take, the CPS 803 Machine Learning and 843 Introduction to Computer Vision. Machine learning, you'll touch a little bit about deep learning, but mostly be machine learning concepts. And in computer vision is all deep learning, where right now you use MATLAB, but in previous years you used PyTorch as well. Then there's also Coursera, which provides lots of free courses. And as I mentioned, Andrew NG, his deep learning specialization. I'm pretty sure that's one of the most popular deep learning courses that people take. Then there's Kaggle, which is basically the leak code for AI. There's problems there. There's free data sets you can use. There's competition. Some of these competitions have prize monies in the thousands. And then last thing is this personal projects, especially for beginners. When you're starting off, you're the way most people learn is just you learn as you go. And when you need something, is then you figure it out, and then you learn that thing that you need. So personal projects are great as well. So that concludes the workshop. You can, if there are any questions, you can ask any question about us, about the workshop, more in depth about some certain topics I talked about. You can ask, why was there a cat in the last slide? That's a pretty important question. You can direct it towards me or Wayne as well. Any concepts? There was a cat there because I like cats. So I needed to put a cat there. Very simple. And you can also rewatch this. It'll be up on YouTube. If you need more advice on specific things while you're learning, you can shoot me a message. So Michelle asks what medical applications can be used. So as far as I know, there's not really any medical application that only uses deep learning. Deep learning is an assistive technology. Now, what does that mean? That means like when doctors are, let's say, reviewing x-rays for your if you have cancer or not, they're not going to solely rely on the deep learning algorithm. It'll be assistive technology. They're gonna look at it. The model might suggest, hey, look here, this might be a tumor, or that might be a tumor. So they use it as an assistive technology. Deep learning can do wonders for you, Z, if you embrace it. And there's also on the medical topic, there's actually, I think it was recently I saw a paper that came out that actually in the field of 3D deep learning, where when you take CT scans in 3D, it works on that level. So that was pretty cool. So the way I learned, I started with Andrew NG's course, but then after I did that, I moved on to Skill because Andrew NG's course is more theory and the math behind it, and you need to be good or decently good at linear algebra to if you're just using like TensorFlow just on like whatever basis, like you're not trying to go too deep into it, then you can go on Skillshare, you can go on LinkedIn Learning, look at people's courses, and especially for there's this guy called Frank Kane. He has a really good course on TensorFlow, using TensorFlow. If you go on Udemy, it's probably like $100. So I recommend getting a Skillshare 1 month free trial and canceling it because his course there is there as well. So Frank Kane. Not right now, Suhavi. As it stands now, Google Colab is actually getting pretty popular in the field people who actually use it. And because what Google Colab does, if it allocates a GPU for you, and as I said before, if you're running this stuff on a CPU, you're not going to see any results. It performs worse. It takes tens of even 1,000 times longer to train in some cases. So you need a good GPU, right? And so Colab provides great GPUs for free. Now there's a time limit on how long you can use it, but if you get a pro version, which is $10 a month, right, then you can get one of the top, like the Tesla V100 GPU, which costs like $6,000 to use, and just for $10 a month. So Colab's really good. But if you're planning to do everything locally, then yeah, you'll need a pretty decent one. Any more questions? All right. If there's not any more questions, we can end it here.
Thanks for tuning
Wayne's
in, guys.
Wayne's
Well, sorry,
DMs are open.
I had
Yeah.
a lot of technical difficulties, but yeah, thanks for tuning in. I hope you guys learned something. Let me know if you can see the link that I shared above. Definitely go ahead and try it out.
Yeah. Both of our DMs are open if you need to ask questions, and
Yeah.
especially Wayne's, his is always open.
Nah. Follow me on
All
GitHub
right.
though.
Follow me on GitHub. Exactly. All right. Thank you, everyone. Bye bye.
Take care, guys.